Hello everybody. Time for lecture 13, which is, I believe, our final taped lecture. Today we discuss the third technique to find the volume of a solid of revolution. This is the shell method. So why you need a third method? We already have the disk method when there is no gap. We have the washer method when there is a gap. That seems to cover all the bases. But why you need the third method is this. Let's say you have this region, right? And you want to rotate this region about the y-axis, right? So it's a vertical axis of revolution. Now we would have to use the washer method here if we were to use one of our previous two methods. But it'd be really hard because the washer method, you stack up rectangles along your axis of revolution. So we'd have to stack up rectangles like this. Like that would be the first rectangle. Right, and as you start to stack them, you start to see some issues. Like right about here, for example, there's an issue. You'll have a rectangle here, a rectangle over there. You'll have two rectangles occupy the same slice horizontally. And then even for these rectangles up here, in order to do this, you have to find equations in terms of y, which would be the variable for a vertical axis of revolution. Find equations in terms of y for this piece of the curve and that piece of the curve. Not to mention two more over there. So I kind of made a mess of my picture. But basically, the washer method would be really hard. Like really hard. We would have to find 1, 2, 3, 4 different equations for this curve so we could do all the right side versus left side stuff. We would have to have multiple rectangles for the same slice. It'd just be a ton of work, a ton of integrals, and a ton of algebra. So instead, we use the shell method. So to recap, the disk method is if there's no gap. The washer method is if there is a gap. The shell method is if those previous two methods are really hard to do. And so here is the thing. This function is best expressed in terms of x, right? This is a function of x, because if your variable is x, you only need your one equation. And so we want x to be our variable. But for a vertical tangent line, the washer method needs y to be the variable. But we want x to be the variable. So that's pretty much what the shell method does. It lets you use the opposite variable than the disk and washer methods. So for the shell method, and then we'll derive how the formula works. One, if the axis is vertical, if the axis of revolution is vertical, for the shell method, you use x. You are in terms of x. And the second possibility for us is if the axis of revolution is horizontal. In that case, you use y. So it is the opposite from the washer and disk method. For the washer and disk methods, when you are vertical for your axis, you're in terms of y. When you're horizontal, you're in terms of x. The shell method flips those two. And again, it's because sometimes those techniques are really hard if your function is not easily expressed in the variable that you're supposed to use. So let's see how this works. So basically, the shell method has this. You have some two-dimensional plane region, and you rotate that region around, in this case, that vertical axis right there. So this gets flipped around going that way. You get like the top half of a donut, perhaps. Now how this works, the shell method, is you make rectangles that have to have the same direction as your axis of revolution. So usually you would line up the rectangles along the axis of revolution. This time you're going the other way. And when you rotate each of these rectangles around, so here's all the rectangles. When you rotate each of those rectangles around, it gives you this. This is the shell. This is a hollow cylinder, right? This right here is our original rectangle. And when we rotated that around, it gave us this empty shell of a cylinder. So, to write that down again, for the graph that we were using for our first example, the graph was kind of like this. You break this up into some finite number of rectangles. That's one of the rectangles. When you rotate this rectangle around, right, it comes out of the page, into the page, it gives you this kind of shape. Whoops, bump in the paper. So it's a cylinder, but it's just a shell of a cylinder because it's totally empty, right? And again, this original rectangle right there shows up like right here. So this was just rotated around. And then how this approximates the true volume is you have a bunch of concentric shells. So like this rectangle right here, this one in blue, when that one gets rotated around, it's like down here. It's like inside of this one. Oh, my blue marker is running out of ink. That's okay. Right, but it's like inside of it. And then there's a shell inside of there. It's like a bunch of hollow shells that are all inside of each other. It's kind of like a Russian doll situation. Right, you have a bunch of hollow shapes inside of each other. This is the same with this method. So now let's derive the formula that we'll use to find volume with it. So we'll start off with our shell. I'm just going to quickly sketch what I had just done again. Alright, so here's our function f of x. Here's an example of one of the rectangles being rotated. We're vertical, so we're in terms of x because shell is opposite. And then when you do that rotation, you get that empty shell of a cylinder. And it starts off kind of being similar to the washer method, because the washer method also had a cylinder in a cylinder. And so our total volume of the solid that we're trying to figure out, the solid formed by rotating this region about the vertical axis, is approximately the sum from 1 to n of v sub I, where v sub I is the volume of the ith shell. Right, and if this is the ith shell, the volume of the ith shell is the volume of the big cylinder minus the volume of the cylinder that's being subtracted. So say, there's our big cylinder minus there's our small cylinder. This is h sub I. Big R is the distance from the center all the way to the outside. Small r is the distance from the center to the inside. Right, so pi big R squared h is the outside cylinder minus pi small r squared h, the inside cylinder. We then factor that. And now the big difference between the washer method and the shell method is h sub I. For the washer method, that was delta x, and that got infinitely small as n went to infinity, so this turned into a Riemann sum and all was well. But h sub I does not do that here. H sub I is a height. Really, h sub I is based off of the function somehow. So h sub I is not delta x. H sub I is not going to approach 0, as you have an infinite number of rectangles. Instead, what's approaching 0 is the width of this shell, right? Because as you put more and more rectangles in here, the rectangles get thinner, and the width of the rectangle is the thickness of this shell. So this is our delta x. Delta x is going to be how thick that is. So we factor this one more step, because that's the difference of two squares, so it's big R minus, or big R plus small r times big R minus small r, and this is delta x, because delta x is how thick the rectangle is. That is the big radius minus the small radius. That gives you the thickness of the shell. So this is our delta x, which we need, because the only kind of sums that turn to integrals are Riemann sums. Riemann sums gotta have that delta x. So we do some rewriting here. So big R minus small r is delta x. H sub I, we can see that the height is going to be a function of x. Like in this particular example, the height is f of x. But either way, the height is going to be a function of x somehow. So we'll call that h of x sub I. It's a function of x, where the x value is in the ith subinterval. And then, likewise, big R and small r, those are also functions of x. Those could be different x values, by the way, because they all converge to the same thing in the end. But I'll just use x sub I for all of them. But if I was being super careful with my terms, I would realize that these could all be different x values. But as delta x goes to 0, it all confirms to the same answer. And so now we have a slightly different expression for v sub I. So the volume of our solid of revolution, which is approximately the sum from 1 to n of v sub I, the volumes of all those shells, is the sum from 1 to n of pi times r plus small r, which is big R of x sub I plus small r of x sub I, times big R minus small r, that's delta x, times h sub I, which is a function of x. And now we can take the limit as n goes to infinity. So the exact volume would be the limit as n goes to infinity of this sum. I'll put the pi right there still. I'll put the big R of x sub I plus the small r of x sub I. I'm going to move delta x to the back. That's usually where it's written. And this is an integral, right? Because it's the limit as the number of rectangles goes to infinity of a Riemann sum. So it's the integral from a to b. Now a funny thing happens. As n goes to infinity, delta x is going to 0, right? Because delta x is how wide each rectangle is. As you get an infinite number of rectangles, that width goes to 0. If delta x is going to 0, it means that these two are approaching each other. Right? As the width of the shell goes to 0, the two radii, the outside and inside radii, approach each other. And so, big R plus small r, we can just write as 2 times one of those r's. I'll just use small r. But I also could have used big R. But the point is that since n is going to infinity, therefore delta x is going to 0, therefore those two radiuses are approaching each other, therefore as n is at infinity, they equal each other. And so it gives us 2 pi r of x, h of x, dx. I'll write that one more time because it's kind of sloppy. So the volume is the integral from a to b of 2 pi r of x, h of x, dx. This is the shell method for a vertical axis of revolution. If it's a horizontal axis, then you use y, because the shell method does the opposite of the other two methods. So r of y, I messed that up. So the integral is from c to d, thus my go-to bounds for y functions. And that's for a horizontal axis of revolution. There's another way to derive that. This was the more formal approach. We made an approximation, made sure that it was a Riemann sum, and I took the limit as n goes to infinity of that Riemann sum, which gave us all the stuff in red and led us to our final answer. We could also have done this now. This is the informal approach that gives the same answer. So more informally, we have all of our shells. That's a horrible job at the bottom. Hold on. If we cut this shell, like right here, we'll say, we just kind of slice through that piece of the shell, we can then unfold it. This pen is trash. We can unfold that shell, and it'll give us something approximately like this. Not quite like that, right? Because the inside radius and outside radius, which are the bottom length and the top length, aren't quite the same, but it's almost this. So it's about that shape. Now the height there is the height here. So that's h, so that's h. This right there is the thickness. That is the thickness of our rectangle, so that's still delta x. This is the result of unfolding that circle. So that is the circumference of the circle. So that's 2 pi r. Now both the height and the radiuses are a function of x. And so when you use the shell method, you're just taking the sum of an infinite number, which is the integral, of the volumes. That times that times that, base times width times height. There's the base, there's the height, there's the width. So two techniques. This one might be easier to do if you forget the formula. Just remember that the shell unfolds to be a little super thin box like that, I suppose, and the volume is base times width times height. And again, it's 2 pi r because that is the circumference. This distance became that distance.